The degree of non-parabolicity of the surface close to a rotational paraboloid. The basis of the operation of all parabolic antennas is the idea of transforming a plane electromagnetic wave into a spherical one, or vice versa, transforming a spherical wave into a plane one. The larger the surface area of the antenna, the stronger the signal that can be obtained at its output. The efficiency of the antenna depends greatly on how close its surface approximates a paraboloid. In the article under discussion, we will take into consideration some convex rotational surfaces omega, which in the Cartesian coordinate system are described by the equation z equals f of x and y, where r squared is greater than x squared plus y squared. The function f of x and y being twice differentiable in the circle D satisfies the following two conditions. Here you can see two conditions, and when function will satisfy the condition 1. It is known that a rotational paraboloid possesses the property of focusing. Rays parallel to its axis of symmetry, optical axis, after reflecting off its surface pass through the focus of the paraboloid. When f of x and y equals 1/4 c times the quantity x squared plus y squared, then all rays which are parallel to the axis of the applicant after reflecting off the paraboloid surface will gather in point F. We can say that a rotational paraboloid is inscribed in a convex surface omega if their edges and vertices coincide. In this case, we will refer to the focus of the paraboloid as the conditional focus of the surface omega. Now, let omega be a certain convex rotational surface with a hypothetical focus at the point F. Let D denote the region in the z equals c plane where all the parallel axis applied rays converge after reflecting off the surface omega. Here's the definition. Let a convex rotational surface omega is described by the equation. We will refer to the degree of non-parabolicity of the surface omega, where D is the area of the region. And here are the assumptions below. The axioms of non-negativity and symmetry for the introduced matrix are obvious, and the triangle inequality is a consequence of this inequality. Non-parabolicity of a spherical mirror. To find the hypothetical focus and the degree of non-parabolicity of a spherical segment omega, we use this formula. The ray reflected from the segment at point K intersects the plane of a hypothetical focus z equals c in the distance mentioned below, from the axis of the segment. The radius p of the circle D is equal to the distance where the ray reflected from the edge of the hypothetical focus intersects the plane of the focus, and it's also mentioned below. At this picture, we can see a spherical mirror of radius r. At this slide, we can see the degree of parabolicity, and at the picture below, we can see track of the rays in a spherical segment that acts as an antenna mirror. Deviation from parabolicity of a wave-like disturbed paraboloid of revolution. Let the parabolic surface located in the cylindrical coordinate system, described by the equation mentioned. Disturbed by the deviation mentioned as well, it remains convex. We will find its degree of parabolicity as a function of the parameter A. And here we can study the surface. The angular coefficient of the reflected ray is shown at the formula below. Distance d of the point of cross-section of the reflected ray and the focus plane z equals c from the axis of application. At the picture, we can see wave-like perturbed parabolic mirror. Focus of the paraboloid is in point F, amplitude of perturbance A equals 0.2 multiplied by C. Conclusions. The proposed approach to assessing the deviation of a surface from a rotational paraboloid allows for the consideration of the efficiency of the antenna surface, taking into account energy losses during signal reception and transmission. This approach can be applied to analyze an antenna system subjected to wind loads and other natural disturbances that may induce random wave processes on the antenna surface.